technique that we are going to learn is known as photolithography. This is one of the most commonly used techniques in microfabrication. Also, for us it is important because the polymers that are used in photolithography, they yield reasonable glassy carbon. Okay, so now forget about glassy carbon for now. In this slide, I'm going to tell you what is photolithography. This is a highly simplified version. So I'm telling you some very fundamental steps of photolithography to give you an idea of what is done. But if you want to learn more about, the optics of photolithography, there are so many NPTEL lectures on microfabrication. So you can then, refer to those lectures for further details. Okay. So photolithography involves the UV light. Now, how does it involve? How do I use light as a tool? Okay, so light can be used as a tool if the material that I'm dealing with is sensitive to that light. You know that there are many materials that are photosensitive. You leave them in the sunlight and something bad will happen to them. They change their chemical structure. That is what is actually happening to them. So you have photosensitive materials. Now photosensitive materials are maybe sensitive to different wavelengths of light. All materials do not have the absorbance at the same wavelength. So there may be different photosensitive materials may be sensitive to different wavelengths of light. Now, in the case of photolithography, we are particularly using the materials that are sensitive to the UV light. And these materials are known as photoresists, or commonly you just call them resist. But these are called photoresists. And you have, now what happens when they are exposed to the UV light? Two things can happen. Either they chemically degrade, or in some cases you may even get larger molecules. They harden because they get cross-linked with their neighbors because of the UV light. So two things can happen, right? So you get a larger chunk of material, or your material completely degrades. So these can be two possible effects of the UV light. And that is how you also then define your resist. The resists can be, or photoresist can be of two types. One is known as negative photoresist and the other one is known as positive photoresist. And I will describe why would you call something negative and positive. So the idea, the definition is that the positive resist would get degraded when it is exposed to the UV, and whatever gets cross-linked after the UV exposure, you will call them, those kind of materials, negative resists. And there is a very minor difference in how you perform photolithography. So first let's talk about the 5 main steps of photolithography. Okay, so what do? You take a, let's say a silicon wafer. Silicon wafer looks like, maybe in the next time I'll show you an image. So wafer is just this very thin, as the name suggests, it's very thin. It's a wafer, and it's typically it's a circular wafer. You can also get square wafers. Those are used more in the case of solar cell fabrication. But for photolithography and so on, you will get these circular wafers. They are typically either 4-inch or 6-inch in diameter. And these are actually single crystals. You can grow really large crystals of silicon, and then you can make wafers out of it. You can slice them into thinner wafers. And then you can, of course, you can also have P doping in the wafers, N doping in the wafers. You have different crystal orientations in the wafers, 100 or 111 plane. Also, you can get these kind of wafers. So again, that's a separate topic altogether. But you take a silicon wafer now, and on top of that you pour your photoresist. So in this picture, this schematic I have shown that. So the gray circular thing, that's your silicon wafer, and the big drop, orange color drop, that is your photoresist, and the arrow indicates that this then would rotate at very high rotations per minute. So you can have, for example, you will typically have above 1,000, between 1,000 and 5,000 RPMs, but typically you would have, let's say, 3,000 RPMs. Okay, so you pour a drop of your photoresist on top of the silicon wafer. The wafer should be clean. So there is also wafer cleaning, can be called a pre-step before spin coating. But assuming that the wafer is cleaned, then you spin coat your polymer on top of it, and then this blue thing which you see in this schematic, that is something known as spin coater. So basically it's a motor. And this motor has also a vacuum chuck, which means that you can attach your wafer on top of it using vacuum. So then this motor rotates at whatever RPM you set, let's say 3000 degrees, and then now what will happen? You pour some liquid on top of a flat surface, and then you rotate it. What will happen? That liquid will convert into a film. So that is what you need. Now you will be working with this film, and the thickness of this film can be determined by setting the correct rotations per minute, and also, of course, it will depend on the viscosity of your liquid. So if your photoresist, let's say, if it is very viscous, in that case you may require higher RPMs to get a certain film thickness, and in the case of very less viscous materials, then even at very low, so you will get thinner or thicker film that can be optimized using the viscosity of the polymer, and then you will make a film. So that is your step number 1, making a uniform film of polymer or resist on top of your cleaned silicon wafer. Now what do you want to do? You want to because your whatever polymer you use may have certain solvent or may have some volatile things. So you want to get rid of them, and that is why you will do certain baking. This baking is for most resists done below 100 degrees. So 65 and 95, these are the temperatures at which you will do the baking of the resist. So you get rid of the solvent, or at least the unnecessary solvent. Okay. Now what happens is, now you want to expose this entire thing to the UV light. Okay. Now will you expose the entire structure to the UV light? Let's say I'm using a negative photoresist here, which means that this the parts that are exposed will become cross-linked. If I expose the entire structure to the UV light, then the entire wafer, the entire film will become cross-linked, and that will become hard. Don't want that. What I want is, let's say I want certain square patterns on top of my silicon wafer. So what I will do is I will make something known as a mask. Mask is typically a glass or quartz, it should be UV transparent. So you will have a transparent, a structure or a film substrate. And on top of that, you will make some black, whatever is shown here, black structures, whatever you need, square patterns or whatever patterns you want. You can have circles, you can have any complicated patterns. I can make my own picture. It doesn't matter, because this has to be just printed on top of the mask, as long as you can print it on top of the mask, which nowadays you would do using any CAD software. So it's not that you're using traditional printing techniques. So it is easy to make pretty much any structures, and hundreds of such structures. So for example, if I need one square pattern which is 5 micrometer by 5 micrometer or 20 micrometer by 20 micrometer square, I can make several such squares on top of a wafer which has 10 centimeter diameter. So that would be then my one entire batch of structures. So I make these structures on top of a transparent material such as glass. It should be 1 transparent and 2 very flat. Because flatness is important. Now we are going to attach it on top of your silicon wafer. It should be as closely attached to the silicon wafer as possible. Why? Because the next step is that you expose this entire thing to the UV light. Now UV light will go only in those regions where you have the transparent parts, where you have the black parts, or not black necessarily, but let's say a metal also can be used, but something that can block the light from going to your polymer. Okay, so through the transparent parts only the light will go. Now, however, where you have the edges of these transparent parts and non-transparent parts, there the light can get diffracted. And that diffraction will actually lead to rough edges in your structures. And that diffraction is what you want to minimize. And that is why what you want to do is you want to have as closely attached mask as possible. This is also one reason why we did the baking before. Because if you otherwise attach the mask, and let's say your material is still, it still has some solvent, it's soft. In that case, what will happen? It will damage your mask. And these masks are reasonably expensive, especially as the feature size, the structure size goes down. The smaller the feature, the more expensive your mask is. Because let's say for up to 25 micrometer structures, you can still use traditional inks or slightly modified inks, not the traditional inks, but still you can use these glass or quartz substrates, and you can do the printing. You can use certain types of printing techniques. But when you want to make structures which are like smaller than 5 micrometer in dimensions, in that case you need to use very sophisticated techniques, and you need to do this printing of masks using certain metals. You use things like electron beam lithography just to make the mask, and you use metals like chrome for making the mask as the inks. So now the mask itself can be really expensive, and also you want to, it's not just about expensive, the fact that you want to utilize it for several batches. You want to have the exact same structures for several batches, so you don't want to damage your mask, and that is why the baking step was also important. Okay. Now you did the UV exposure. Now, will you have any dose of UV? No, the dose of UV light also you need to optimize, because now your material can cross-link when it is exposed to the UV light, or degrade also. Now, how much, if the film is too thick and I have not exposed it for long enough duration to the UV light, then maybe only the top part will get cross-linked. Or if I overexposed it, then it might happen that the top part will give me a T-like shape. So you have the straight walls, but on top of that there is too much cross-linking. This is called T-topping, in fact. So overexposure and underexposure both are bad for the structure. So you will optimize. Now for every photoresist, typically the manufacturer will give you the instruction what film thickness requires what dose of the UV light, and then accordingly for the intensity of your own whatever UV lamp that you have, or UV or if you have a machine which has you have something called a mask aligner, which can align your mask on top of your wafer. So your mask aligner or your simple UV lamp, whatever you have, the intensity of lamp you need to know, and accordingly you can calculate for how long do you want to expose your sample to the UV light. Okay, so this is kind of the most important step, and that is the step number 3. I have written 3A here. 3A is done only for negative resist, which cross-link when exposed to the UV light. Now why? Because if a material is just degrading when it's exposed, then it's okay, it degrades, and then you're done. But cross-linking is initiated by the UV light, but you may not get complete cross-linking. For that you need to heat it. So actually cross-linking propagates during this other baking step, which is known as the post-exposure bake. So that is only done for negative photoresist, and then what you do is you develop these structures. So what is developing of the structures? You put it inside a chemical. Now that chemical will selectively wash away the degraded part in the case of positive resist, or the uncross-linked parts in the case of negative resist. So now you have a certain chemical which is specially dissolving one type of the polymer. Okay, so what will happen now? Your here is the picture. So you basically put your entire wafer inside this some structure, and then what will happen is some parts selectively will get removed, and the other parts will remain, and that is how you have your structure. You will typically have a lot of structures on one wafer, and then you will do the inspection. Okay, you are able to get what you made or whatever. Then you can do the further processing with these structures. In our case, when you want to make glassy carbon structures, now you're going to take these structures on silicon wafers, either the entire wafer, or you can cut it into smaller pieces if it's a batch fabrication technique. Put it inside the furnace, and make sure it's a tube furnace and you have an inert environment, and then heat it up to what temperature now? Well, 900 can already give you a reasonable carbon if the structure size is small enough. If it's in the micro domain, typically 900 gives you reasonable carbon, reasonable glassy carbon. Now, there have also been questions about whether or not this material should be called glassy carbon, because traditionally what is called glassy carbon is prepared at 3000 degrees, and many people still believe that it's not just about the removal of the impurities, it's also about the kinetics of carbonization and graphitization, which may not be possible at temperatures as low as 900. But here is the thing, the material that we obtain at 900 degrees, it has properties very similar to glass-like carbon. For example, so number one, it's prepared by coking, so it has flat surface. That is something which is very important for us. In fact, in this case, the surface is even very, very uniform and flat because you prepared it by spin coating. So you see this photolithography technique, you already prepared an extremely flat film. And all your structures are film-based structures. They have a flat surface. You're working with liquids from the beginning. Even the resins are not solid resins. You're working with liquid. So you already have a very flat structure. And because if you have, let's say, a phenol formaldehyde resin which undergoes coking, then in that case you will get very nicely atomically flat surface. So that property, of course, is there in these structures. Other things such as electrical conductivity, that is also within the same range as what you have for large-scale structures. Mechanical, so Young's modulus is also in the same range. So most of the properties are similar to glass-like, commercial glass-like carbons when you get glass-like carbon from photolithographically patterned structures. Now, specifically in this particular case, I would like to mention a commercial name. I don't like to use commercial names, but there is a type of photoresist which is known as SUH. Which I'm using this name because this is the polymer that gives you a good quality glass-like carbon. It is known to give you a good quality glass-like carbon, or the carbon that is very similar to properties of commercial glassy carbons. Okay. Now, however, having said that, there are other polymers that have also been tried out for giving whether or not they yield glass-like carbon. So there have been, you can read there are several papers. Okay, so the point is that the material should undergo coking, and in the case of microfabrication, these specialized polymers resist. Sometimes you don't know what is the exact chemical structure of a resist. So in the case of SU8, we know it's a type of phenol formaldehyde resin because these resins are already traditionally used for making glass-like carbon structures. You know that all these larger structures also use these resins. So it was already expected that this will give, a similar material at micro scale as well. And that is why this resist became very popular for yielding glass-like carbon. But there are also other polymers, maybe if you don't know their chemical structure exactly, then what you can also do is you can, for example, you can perform certain experiments, you can make structures that you want, that are very sharp, let's say, conical structures, and then you see, how much does the tip bend on carbonization if you have very thin tip. That means the structure, the material is going through coking. But at the same time, it might be going through so much coking that you are losing the shape. So you can do multiple experiments. You can take the tip and keep it, upside down also and see if it elongates. The best case scenario is that when your material goes through a semi-solid phase, but not so liquid-like phase that it loses its shape. And phenol formaldehyde resins are traditionally used for this purpose. Traditional glassy carbon precursors, since the for a very long time. Okay. Now, so these were the 5 steps of photolithography. This is something, as I said, that this was a very, very general idea of the technique. There are a lot of things involved when you are doing the UV exposure, for example. Then you can also make multi-layer structures. So you make one layer. You make certain, let's say, these square patterns. On top of that, you want to make something else. On top of that, you want to make something else. In that case, you will require these machines known as the mask aligner, where you need to, when you're making the second layer of your structure, then you need to align it very well with the first layer. Because otherwise, you may end up, having some certain offset in that is very undesirable. These micro scale structures you cannot really see through the naked eyes. When they are very small, and you can, so for alignment you need these, microscopes, and that is why you have this overall setup. You also have UV exposure you can perform using this mask, through the mask. You also have something known as maskless lithography setup, where you don't have a, physical printed mask, but you design it in a certain software, and then through that you expose the UV light to your structures. But there are many variations and there are many advancements that have already taken place in the case of these of the UV exposure step, most importantly. You can make very small structures in different types of mask fabrication techniques are also available and so on. So that you can, and also the optics of these instruments is also very interesting. You can have complete contact of your masks. Sometimes you can also have slightly, there's some proximity. Your mask is in the proximity of your wafer, but not completely touching. Let's say that would you would do that in the case of a polymer where you cannot avoid certain liquid part, or polymer does not become hard before the exposure, so you don't want to attach the mask into it. So there are many other things. There are many other techniques, the details of photolithography. But at the end, what you're getting is these kind of structures now on top of your silicon wafer. Now here one more small thing that I would like to mention, so negative and positive resist. Why the terms negative and positive are used? Because so you see in these images, you will see that if you have a positive resist means this will degrade on the UV exposure. So what you will have is the structure that you want to make. You will have the same structure on your mask, because whatever is not that structure, you want it to get degraded and washed away with the developer. So in that case, you have sort of the same structure, so you call it positive. You have the positive structure on the mask also. In the case of negative resist, you have to have the opposite structure, because the parts now that are exposed to the UV light will stay there because they become cross-linked. And it's the uncross-linked parts that will be washed away with the developer. So in that case, what you will do is you will have the negative of your actual structure on top of your mask. And that is why the name negative and positive, these are the terms that are used. Okay, so now what is the next step? You have a photoresist, you perform photolithography, you get some microscale structures, and now you take your entire silicon wafer or the pieces, put it inside the furnace, heat it at 900. Now, why 900? There is one more important thing. So, why don't we go to 3000 degrees? Why can't we make better carbon? We know that if we increase the temperature of the carbon, it will increase the cost of the overall, process. That is true. It's energy consuming and so on. But at the same time, you may get higher graphitization. Higher graphitization means higher order. So now this glass-like carbon is a non-graphitizing carbon. So it will never convert into polycrystalline graphite. Don't keep that in mind, because you always have these curved carbon structures. You always have these fullerene-like structures that are not going to give you 100% graphite. You're not going to get even polycrystalline graphite. You're not going. That is why they are called non-graphitizing. But then, why do we talk about graphitic content in them? Well, some parts do have graphitic ordering. They may not have the ABABA arrangement. They may not have the exact graphite-like crystal structure, hexagonal crystal structure, but they do have these graphitic sheets on top of each other. They may be randomly oriented. Random orientation is known as turbostratic arrangements. So these are turbostratically arranged carbon structures that also contain some curved carbon structure. Now you can also again think of your the models that we had discussed. So there is a coexistence of curved carbon structures along with these larger sheets which have turbostratically arranged carbon sheets. And in some cases, if you keep on heating it, let's say if I said that if I heat it to 3000, these turbostratic sheets, not the curved carbon parts, but the turbostratic part does have a possibility to convert into graphite or to become more graphitic, which would give you slightly higher electrical conductivity, maybe also better mechanical properties. But why don't we do it? Number one, is it worth it? I don't even, it depends on our application, how high do you want to go with electrical conductivity. But even let's say electrical conductivity was very important to us and, if we heated the device, that would be better for us. But still, the problem here is that you have a silicon wafer. You need to now also make sure that your wafer, your substrate, does not melt and does not get deformed even. Does not get deformed by thermal fatigue even. So now the melting point of silicon is 1410 degrees centigrade. But if you have, because when you're performing this heat treatment operation, then you are heating it very slowly. You're heating it at like 5 degrees centigrade per, or lower than 5 degrees centigrade per minute. That's your ramp rate. So you have, this process goes on for several hours, and also when you have the highest pyrolysis temperature or carbonization temperature, 900 for example, then you would keep your material at 900 for an hour, at least for an hour. And then you may also have a nice ramp rate for the cooling, because you also know that cooling does make a difference to the microstructure of your carbon. So this may lead to certain thermal fatigue. So that basically means your silicon wafer may even melt or at least slightly deform at a slightly lower temperature. So to be on the safer side, you would never go above 1200 degrees in the case of microfabrication. Now you are also here and there you can also use other substrates which are high temperature withstanding substrates. You can so people have used for example steel substrates. People have used also sapphire and quartz substrates, but not all of them can go to higher temperatures. So depending upon your application, you can choose the right substrate. In the case of silicon wafer, silicon based technology is very widely available, because also this is used for in the IC industry. So the thin film technology for silicon wafers is sort of already available. These spin coating techniques, but all these machines are easily commercially available. So that is why silicon, and also the best thing about silicon in general, also for its popularity in the IC industry, is the fact that you can grow films on top of it, silicon oxide films or silicon nitride films. Silicon oxide can be easily grown just by keeping the silicon wafer inside a oxidation furnace, what is known as. So you have oxygen there and high temperature. So silicon, the top layer of silicon itself converts into silicon oxide. Interesting part is that this oxide layer is electrically insulating. And sometimes you can create certain windows in this layer also by using lithographic techniques, for example, and then etch the oxide through that window. So you can selectively get parts of your wafer which are electrically conductive and parts that are not. Also, by changing the doping conditions of silicon, you can have different types of whether or not you want it, whatever electrical conductivity do you want and under what conditions, that can also be controlled. So silicon wafer, since it has already been used a lot in electronic devices and semiconductor devices, that's why typically that is what is used. But if you want to just make a carbon structure where you don't really care about the properties of the substrate, then you can also use other substrates. Or even when you care about the properties of the substrate, depends, you can even choose a glassy carbon substrate. So if you remember, I had shown you this film of glassy carbon, a plate of glassy carbon. You can even use that as a substrate for your for your entire pattern. In that case, you can go to higher pyrolysis temperatures as well, higher carbonization temperatures as well. So you can play with all of these parameters, and then you can come up with the devices. The most common the parameters that are used for glassy carbon based microfabrication. So these parameters are: number one, you use silicon wafers with or without oxide films, depending upon your application. Number two, you use this photoresist, which is a phenol formaldehyde resin, which is a negative resist SU8, and it is available in different viscosity. So typically that is what is used. You use 900 degrees centigrade pyrolysis temperature, ramp rate of less than 5 degrees per minute, and you use the inert environment for pyrolysis, and now you get your carbon structures. Remember that these structures will be dimensionally smaller. They will be shrunk. That is the same problem that is, we also have it in the large scale manufacturing. You end up losing some material because it becomes smaller. But here you can even utilize that fact, because smaller structures will have a higher surface area. So smaller the better in the case of micro nano fabrication, right? So you can even sometimes carbonize micro scale structures, and now you get nanoscale structures. So you did not really have to use a fabrication technique which was usable for nanoscale. You could just convert your micro scale structures into nano. So even that can be used as an advantage. The wastage of material is not that big a problem in the case of micro scale, because overall the usage of material is less, much less compared to what you have in the large scale structures.